I want to speak about overconvergent cohomology of modular curves, which well, is something which has to do with p-adic modular forms or p-adic automorphic forms. And so I want to relate them to coherent sheaves on spaces or stacks of Galois representations, with that's something to do with kind of local global compatibility in some envisioned categorical p-adic local Langlands program. So that's kind of the context. And I want to start with stating the main result. And then in the later paragraphs, trying to explain all the ingredients in the main result. So let us fix some K, which is a level group in GL2 of the finite adels, and maybe it should be decomposed as the product of compact open subgroups over the params L in GL2 of the finite adels, compact open. Let's first assume that, or let me fix a prime. At the prime P, I want to fix Iwahowi level. So I want to fix that K at P is I, the Iwahowi subgroup. Well, G, which is GL2 of QP. For me, that's supposed to be the Iwahowi or standard Iwahowi. I want to fix its decomposition. No, sorry. I want to fix a compact version of the Borel in there, B0. So my GL2, my group GL2 should contain a Borel, or did contain a Borel, maybe the standard upper triangular Borel that I write as P times N. This is a Borel. It's unipotent radical. And maximal torus. And then I have the compact versions of this, which is kind of T naught times N naught in here. These are the ZP points of B, T, and N. Okay, so these are the QP points of something, and these are the ZP points of something, so are the compact open variants of this. So that's my situation at P. And then I want to look at the modular curves, or the modular curve of level K. So let YK denote the modular curve of level K. I'm interested in certain p-adic cohomology groups of this. Okay, so interested in the cohomology of YK with coefficients and some p-adic coefficient systems. Okay, and I will introduce these coefficient systems in a second, but let me just say right away that these coefficient systems are constructed so such that the cohomology in some sense interpolates p-adically the usual classical cohomologies that you would attach to finite or to algebraic representations of GL2. Okay, so that's the idea, and let me introduce these coefficient systems. So let maybe L over QP be a finite extension. And I will write down two closely related coefficient systems, which are constructed from representations of the Iwahowi subgroup of I. An extension, and I want to fix a continuous character of the compact torus into the units of L. So that's a continuous character. then attached to this character, I can construct the following representation of the Ibarhori subgroup. So that's supposed to be the induction from the compact Borel to the Ibarhori of my character kappa. And it's a specific kind of induction. So it's supposed to be locally analytic induction. So let me just write this down. So I take all L-valued functions on the Ibarhori, which satisfy this usual relation. F of BG is kappa of this chalk is not so stable. Of the class of B times F of G, B in B naught, and G in the Ibarhori. But I do not take all possible functions, but I just take those functions that are locally on I given by convergent power series. So locally, I looks like a four-dimensional unit ball, and then I know what it means to be kind of some Tate power series, which gives you a function with values in L. Okay, so these are the so-called locally analytic functions. So F is supposed to be locally analytic, which means that locally on I, the function F is given by a convergent power series. Okay, so that's a nice representation of the Ibarhori. So it's a so-called local analytic representations in the sense of Schneider and Teitelbaum. Okay, which is something that I have for every fixed continuous character kappa. But in some sense, I can also take the universal construction, taking, well, in some sense, the universal continuous character. The universal continuous character will not be locally analytic, so there is it doesn't make sense on the nose. But what does make sense on the nose is the following thing: instead of kappa as representation of T naught of the compact torus, you can take the representation of T naught on the space of all functions on T naught. Okay, so I take here the space of all L valued or QP valued locally analytic functions. So this is a space of all locally analytic functions from T naught to QP. And certainly my group T naught acts on this, and then I can induce this and get some nice representation of the Ibarhori. Yes. Well, the question was whether this is all local analytic functions on I. It's not. It's like the on N naught in some sense. You have still some invariance under N naught. Yes, right. That's right, but I want to write them in a similar fashion as up here. That's why I'm doing it this way. Okay, and I maybe should have written that my modular curves are maybe over Q bar or let's say over C, so that it's easier to convince you what kind of local systems I construct, because over C, it's kind of straightforward that out of a representation of I, you can construct a local system or some coefficient system. Okay, so attached to, so for star being either some character kappa or this universal guy, we can attach to this representation of the Ibarhori. We can attach some coefficient system, curly W star, to the coefficient system over my modular curve. So we call that I certainly have fixed some level away from P, and at P I have Ivahari level, and hence out of a representation of the Ivahari I can cook up a coefficient system, which is certainly huge. Okay, that's a system of QP vector spaces, which is infinite dimensional, and yeah, right. I mean, like it's a co-limit of kind of Banach space local systems, if you want to put it like this. And what I'm interested in, as I said, there's a cohomology with coefficients in this. So we are interested. The cohomology, let's say, let's just take H1 from the start to not make this too complicated, or to make it easier for me to write. We are interested in these cohomology groups. Let me just add justification why I'm interested in this. So by the way, this is these are the overconvergent cohomology groups from the title. Okay, so. I'm actually not quite sure whether this is a nice name, but I'm following the terminology of Ash Stevens and David Hansen, who wrote this down and also wrote this down in some great generality. I mean, what's overconvergent is in some sense the coefficient system, because I'm not asking for any precise region or radius of convergence of these power series. What's the ground field for what? Like if you, let's say I take my modular curve over C and just take singular cohomology, and then the base field for the coefficient systems is QP. And in some sense, you should descend this over Q bar and then maybe even have a Galois action and so on. But I maybe make a remark how you can view this in a second. Okay, so I want to add a remark why you are maybe interested in this. So the first idea is that if we take the universal guy, this interpolates all the one for the fixed kappas. So p-adically interpolates these ones. I mean, it's more or less clear, I guess, that these are contained in here, because if you just take kappa as a L-valued function, then this gives you an embedding of the character into the space of functions. So this p-adically interpolates these, and what you actually maybe want to interpolate p-adically is the cohomology with coefficients in the kind of classical coefficient systems that are attached to algebraic representations. Okay, but if kappa is an algebraic character, then this representation W kappa contains the irreducible algebraic representation of highest weight kappa. Okay, so if kappa is algebraic, then W kappa contains the irreducible algebraic representation of highest weight kappa. So in a sense, let me just put it into quotation marks because there's not much meaning to this without making it more precise. The H1 of the universal guy interpolates p-adically the cohomology in with coefficients in the kind of classical coefficient system, the kind of classical cohomology of modular curves. Okay, that's in some sense how this came up and why this is a well-studied object. All right. So let's see what kind of extra structures do we have on this cohomology group. Okay. So so we have some Haeckel action. On the H1 Y with coefficients in these coefficient systems. So away from P, we take just some Haeckel algebra that I want to call H. That's a Haeckel action away from P, which maybe is a commutative Haeckel algebra, which is just given by selected Haeckel algebras at all the places where my level away from P is hyperspecial. And then there's also an action, and also a Haeckel action at P, which is given by what's classically called Atkin-Lehner operators, but which is just the action of the following explicit ring. So I take QP and I take the algebra on some abelian monoid T plus, that's the Haeckel action at P. And what is T plus? Where T plus is the set of all elements of the torus T, such that if you conjugate the compact unipotent radical of the Borel, or the unipotent radical of the compact Borel, maybe this way around, then it's not preserved, but it's still contained in and not. Okay, so that's subset of T, which is an abelian monoid, which certainly contains the compact torus, but in fact is larger. And you can easily write down, or not so complicated to write down, that this monoid T plus still acts by Haeckel correspondences on my cohomology group. Okay, so this acts by Haeckel correspondences. Right? T is my chosen maximal split torus in GL2QP. This thing usually is called the Atkin-Lehner ring, or maybe if you divide out T naught from T plus and then from this semi-group algebra, then it would be called the Atkin-Lehner ring. Sorry? I don't understand the question. Okay. Okay, so there is this Haeckel action at P that we are interested in. All right, so what I want to do is I want to understand this cohomology together with this Haeckel action, and I maybe will at least partially neglect the Haeckel action away from P and focus on the story at P. Right. Right. And well, let me, before stating or trying to state the theorem, let me do a further remark. For those of you who maybe don't like this overconvergent cohomology too much, but do like completed cohomology of modular curves, you can rewrite this cohomology group in terms of completed cohomology. So in terms of completed cohomology, You can rewrite this. So let's take the kappa variant first. So there is a thing called conjecture cohomology, which I will not define, but either assume that you know it, or tell you that you shouldn't bother about this remark, which is a Banach space representation of GL2QP. So you can pass to its locally logic vectors. After this, you can take the invariance under N0. Sorry, I should have started with the universal guy first. Okay. And you see that on this guy, you have an action of T plus via as follows. So you take some element T and T plus and some vector and this N0 invariance. And what you want to do is you just want to act by T. The point is you might lose invariance under N0 because T is not normalizing N0, but at least it's kind of normalizing N0 up to things of finite index. So you can average about this. Okay, so you can actually make this invariant. So you can take NTV where N runs over representatives of this finite quotient. Okay, so that's how T plus acts here. And via this formula, you can also explicitly read what this action of the Hecke operators at P is. Okay, so this is how you recover the universal guy. And for a fixed kappa, you just take the eigenspace where the compact torus, which sits in here, acts via kappa. I think I don't have to do anything, but Vitas wants to do something, but I don't know what he wants to do. I mean, is it about this or about that? Okay, like, what's the question? No. There's no ordinary part, there's no finite slope part, it's just like this. I mean, I will take the finite slope part in a few moments, but for this description, it's not necessary. Okay, and the kappa version is in some sense just recovering the part where the compact torus acts via kappa. And the second remark is, I'm destroying a lot of chalk. The second remark is that there is a relation to a more classical approach to p-adic automorphic forms. So there is a relation to a more classical approach to overconvergent p-adic automorphic form or p-adic modular forms. Okay. Yes. Okay, thank you. I was asked to just use a better chalk. But as I was quite sure that I would destroy some chalk, I didn't want to use the good one. I will try. Thanks. Okay, and I will not kind of state a precise relation, but just give you the idea how this comes about via some kind of overconvergent Eichler-Shimura maps or Eichler-Shimura isomorphisms. So if you take some kappa, this one, and tensor this up with CP, then at least for generic kappa, this should have a Hodge-Tate decomposition. So I'm secretly using that you have some Galois action here. I didn't really tell you how this comes about, but for example, you should be able to construct a Galois action on this guy using the comparison with complete cohomology that I just wrote. Okay, so that I don't need to argue how to construct a cohomology with these huge coefficient systems. Okay, and let's say kappa is a pair of two characters, kappa 1, kappa 2, which goes from T naught, which was just VP star squared, to, well, say QP star or L star. Let's not be too precise for this remark. Okay, so you can look at the Galois action of this on this, so semilinear CP action. So this has a Hodge-Tate decomposition. So this has Hodge-Tate weights, let's say kappa 1, and so the first one is the weight of kappa 1. So the derivative of kappa 1 at 1. And the second weight is the weight of kappa 2 minus 1. There's this usual shift between highest weights and Hodge-Tate weights going on. And the weight kappa minus 1 part, so the part for this, so the weight kappa 2 minus 1 part is related to some kind of M kappa dagger, more classical way of writing down p-adic modular forms as sections on line bundle on some overconvergent regions and so on. Tensor CP. Okay, by some overconvergent Shimura maps, that's kind of the buzzword I should put here, and maybe quote Andreatta, Jovita, and Stevens, who maybe gave first constructions of things like this, and Juan Esteban Rodriguez Camargo, and maybe also Louis Pan, who in general wrote down some kind of Hodge-Tate decomposition of complete cohomology, that you could also view this as some kind of special case of. All right. So that's the object. Well, on the side of modular curves. Which describes the first half of my title. So let's see whether I can say something about the second half. All right. So let's try to relate this object to something cooked up from Galois representations. Okay, so assume, for simplicity, I'm sorry, I need a longer chalk. That KL is maximal compact for all L not equal to P. Okay, this will just make it easier for me to write down the statements. And I want to write X odd. This is supposed to be the stack or the rigid analytic generic fiber of the stack of all odd two-dimensional GQP representations. Representations of the up to two-dimensional p-adic representations of the absolute Galois group of Q, which are anomified outside P. Okay, so what you should think of is to take a disjoint union of universal deformation rings, which is kind of a disjoint union of formal spectra of complete local rings. You take the generic fibers, which give you some nice rigid space, and then you divide out by the kind of choices of framing that you had for the deformation rings. Okay, so it's a kind of really nice or like well-behaved objects. And then I want to state the following theorem, which is joint work with Zhixiang Wu, and it's in progress. So not all details written up, which says that after localizing at a non-Eisenstein ideal at ideal M in the Hecke algebra away from P, maybe plus satisfying some technical Taylor-Wise assumptions that I will just swap under the carpet. I want to compute the chromology with coefficients in my coefficient systems. In terms of Galois representations, I can't quite compute the raw chromology. I can only compute what's called the finite slope part, and I'm going to explain this in a minute. But this is supposed to be given by the cohomology of some coherent sheaves on the space of Galois representations, on the stack of Galois representations. And I will just write down the formula and give you the description of the ingredients in a second or maybe a bit later in the talk. So I'm trying to construct an explicit coherent sheaf on the space X odd. Sorry, I don't want X odd, but I want to take the product with a space called T hat. G upper star of pi lower star of alpha upper star of some coherent sheaf F star twisted by a line bundle L 0 minus 1. And you don't have to take cohomology, but cohomology with compact support. So there should be a long list of explanations. What are the objects in this formula? I only want to claim that it is equivariant for the Hecke action, or maybe for Galois and Hecke action. And as usual, I forgot the Galois action on the right-hand side. So what you have to do is write smaller so that it fits in there. G upper star, pi lower star, alpha upper star, F star, tensor, line bundle, 0 minus 1. And then this whole coherent sheaf I tensor with V universal, which is the universal family of Galois representations on the stack. Okay, so I squeeze it in here. Okay. So here I defined my Hecke action. I briefly told you that you should, in some sense, at least by comparing with complete cohomology, get some Galois action. So it's clear how Hecke and Galois act here. Here, Galois certainly acts via the universal family that I put here. And at least the Hecke action at P will in some sense be evident from the way I've written down this coherent sheaf. Yes? I mean, okay. I would R gamma C. So the question was whether this is just concentrated in 1 degree. So in degree 1, actually, if I just write H1 here, I want to view it as a single group, and hence I would like this to be considered in degree 0, but that's kind of just a matter of taste. I would R gamma C instead of just gamma C or H2 gamma C or H2 is compact support or something like this. Just because depending on what star is, this cohomology will fit in different degrees. And actually, I will have to shift, like the way I write down this F star will in some sense take into account the shift of degrees, so that in the end, this will just fit in degree 0. Okay, so let me try to write down. Well, first of all, on the left-hand side, this Fs is the finite slope part. With respect to the local action. So, like see below for a detailed explanation. But the idea is that you want to invert the action of the UP operator. Okay, so in quotation marks, I want to invert the action of UP, which is P1, which is in T plus. Or it's a subspace where this is invertible, roughly. And it's strictly speaking, maybe not even a subspace, but this is the idea. Okay, so let me start by trying to explain what the sheaves on the right-hand side are. So T hat is the space of continuous characters of T. So the rigid analytic space of continuous characters of T, so which I can write down as the hom continuous of T into GM of something. So it's a rigid space representing this functor. Okay, and which I also can identify with a continuous character on T naught. And then extend this to a continuous character of all of T by just specifying the values of the uniformizer. So it's can be decomposed. It's isomorphic to non-canonically, that is up to the choice of uniformizer, to T naught hat times GM squared. So T naught hat, of course, being continuous homs of T naught. I mean, the rigid space representing this functor. And now in the second paragraph of the talk, or the second part of the talk, I want to explain what these sheaves here are. Okay, so what these maps G upper star, pi lower star, I alpha upper star, and so on are. All right. So let's talk a bit about stacks of Galois position. And before going on, let me say one word about this. Well, following the idea of kissing and then using maybe work of Emerton and also Colmes, I guess, it's been kind of known for quite some time how to describe kind of all the eigensystems that occur in this space purely in terms of Galois representations. That's kind of some kind of overconvergent variant of the Fontaine-Mason conjecture, saying that an eigensystem occurs in here if and only if it's identified almost everywhere and triangular net P or something like this. That's something that's been known in and where at least kind of conjectural generalizations are known. But what's kind of new to this thing is that you can not just describe kind of eigensystems that occur in here, purely in Galois theory electrons, but kind of the whole space together with the space together with this Galois and Hecke action, just in terms of Galois representations and sheaves on space of Galois representations. Okay, so that's what this theorem does for you. And I should mention, at least I announced this in the abstract, as in Kissin's case, for let's say, you can more or less easily conjecturally generalize this formula to other Shimura varieties by the modular curve. Okay, so it's kind of at least kind of as far as the story only at P is concerned. If you maybe in addition assume that your group is split at P, then it's not so hard to figure out that you can write down a generalization of this that works in general. Okay, but like the proof certainly uses p-adic local Langlands and hence only works for GL2QP. Yeah. So Vitas is asking whether, if one knows this theorem, whether it implies something about the eigenvalues that appear in there, and let's say in which sense.
What you said, you got the Galois representation associated for overconvergent modular forms. You can always you have this result more abstract. Well, so would you be just whatever?
Well, from this thing, one would be able to deduce what Emerton proves, and there the answer certainly should be yes. But in some sense, kind of some version of things that Emerton proves certainly also go into the theorem. So, I mean, let's discuss the details maybe later. Oh, I just was hiding M. I mean, like here I would kind of localize like M is my fixed non-Eisenstein ideal. I would localize here at M. That's why just like after localizing at and just erase it from the statement. And here, maybe corresponding to M, you would have some connected component of that space, and you would just kind of take the sections on that connected component. And maybe some more technical things that I should mention is that this is kind of up to this slightly stacky issue. This looks like a Stein space. It's the original Stein space. Okay, and compactly supported chromology for coherent sheaves on Stein spaces was already developed by, like I guess, started by Carriolotto, and then Van der Put did things, and other people did things. But to have a very general formalism of this, I guess now you have to rely on the work of Clausen and Schulze to make it kind of possible to talk about compactly supported chromology of coherent sheaves on rigid spaces in full generality. Okay, but like for the space that appear here, it would be in some sense safe to go back to Carriolotto's explicit construction and just rely on this. All right. Further questions before I explain what actually is written on the right-hand side? Okay, then let me try to explain this. There's the following diagram. So we have this space X odd that I more or less defined already. And I want to take the product with T hat. And then I have a map G, which goes to X, XQP, 2. Well, again, times T hat. And then there was a map pi from something called xv bar. And then there was a map alpha, which goes to something called xt. And this t is at least something I can already write down explicitly. It's the stack quotient of this rigid space T hat that I put over there by the trivial action of GM squared. That's the quotient. It's the stack quotient for the trivial action. Okay. So what I want to explain are the players in this diagram. But before explaining the objects, let's maybe just explain the sheaves, which are kind of constructed from sheaves over here. Okay. So first of all, I have this line bundle L0 minus 1. So the line bundle on T hat mod G at GM squared corresponding to the algebraic representation 0 minus 1 of GM. Okay, let's go. The algebraic character 0 minus 1 of GM squared. This gives me a line bundle on the stack, and I can twist coherent sheaves by this line bundle and then pull back, push forward, pull back, and so on. Okay, and now the F star. So if star is a universal thing, the sheaf for the universal guy, F universal, is just the structure sheaf, but moved to chromological degree minus 2. Whereas the F kappa is just the structure sheaf. Well, I mean, like this is kind of T hat here. T hat I wrote down somewhere over here. T hat can be written as is T naught hat times GM squared. And my character kappa is an element of T naught hat. Okay, so kappa was a character of T naught to L star. So this is an element of T naught hat of L. So what I take is the structure sheaf on kappa times GM squared. But this time in degree 0. Okay, so these are the coherent sheaves that occur, and I'm only left with explaining what the objects are. Well, only. So here, my XQP, or XQPD, is a stack on widget spaces. Mapping, say, A to so-called Zeigarnik modules over the Robber ring with coefficients in A. So to the group set of rank D Zeigarnik modules over the Robber ring with coefficient in A. If you don't like the Robber ring or you've never seen it, then maybe a nicer or smoother way to write this down is to write to say that these are rank D Gal QP equivariant vector bundles on the Fark-Fontaine curve product over QP, so just a stupid product over Q of adic spaces over QP with my widget space by A. So this is the Fark-Fontaine curve. Okay, so the Fark-Fontaine curve is an action of the absolute Galois group of QP by construction. I mean, it's an absolute Galois, the Fark-Fontaine curve constructed out of QP. So it comes with this action. So it makes sense to ask that a vector bundle is equivariant with respect to this Galois action. And that it's of rank D, and maybe you also should put some kind of continuity constraint on the Galois action that I'm kind of ignoring here. Okay. So this gives you one thing, and the map G up there basically should be given by restricting a Galois representation to a decomposition group at P, and then passing from a representation to the attached Vergara module, respectively to the attached equivariant vector bundle on the Fark-Fontaine curve. Okay, so that's describing you one thing. The second thing is xt and xb. So these are the stacks of equivariant vector bundles with a B structure, respectively with a T structure. Okay, so those are stacks of equivariant vector bundles with B structure, respectively with a T structure. Okay, and well, so how does the isomorphism of xt come about? So xt certainly, by writing t as a product of qp star times qp star, can be identified with x qp1 squared, and using a result of Kedlaya, Potthast, and Zhao, you can actually identify x qp1 with the space of characters. That's kind of the home. In my notation, it's qp star hat, so the space of continuous characters on qp star, and you divide by the trivial action of gm, which in down-to-earth terms just means that every rank 1 Vergara module can be written as some explicit Vergara module constructed out of a character times a line bundle. The line bundle just comes about by dividing out by the trivial action of gm. All right. Yes. Yes, right. And I will write xb bar over there. I mean, I didn't explain so far what xb bar is. That's right. I just wrote down some xb. Oh, xb bar. This is supposed to be contained xb, and it's a so-called Greenfeld compactification of xb. Okay, so let me write down a bit more precisely what this is. So actually, what you would like to write down is something that maps sphere A to, well, something in here in xb is a rank 2 Vergara module together with a filtration, so together with a sub Vergara module of rank 1. Okay, so let's write this out. So what you get are pairs D, sorry, in X QP2 and a tuple D1, D2 in X T together with a map. Map D1 into D, which is universally injective, which you can phrase by saying that the co-kernel is flat over A. And I want to ask that the determinant of D is a tensor product of D1 and D2. Okay. Together with a map like this and an isomorphism like this, if you want. And if I would have asked that the co-kernel is flat over the Robber ring, not just over the coefficient itself, then I would have just written down what XB is. Okay, but this, like allowing this co-kernel to degenerate in some sense, should give you some compactification. It doesn't quite give this compactification. Well, for kind of reasons which have to do with equivariance and hot state rates. So what you actually have to take is the closure of XB in this thing, which I call maybe XB naive or XB bar naive. It's a naive compactification in which XB bar certainly embeds. It turns out that it's not dense in there, so you just kind of force it to be dense. Okay. And that's maybe what qualifies as some kind of compactification of the stack of equivariant B bundles. Sorry? What's the structure sheaf on this closure? What does it mean? Yes. Right. So, well, I mean, I will write down something in for something more like in order to make this process of technical closure more precise. I will write down a theorem in a second, but you equip this closure with a reduced structure. Yes. Sorry? Well, the question is whether this function is representable, and the answer is that like this XB and this XB bar naive are kind of explicit groupoids, and these groupoids are rigid analytic Artin stacks. That's what will be the content of what I will write. Sorry? Like in the first place, I also didn't understand Peter's question, but I mean, like, I'm taking some kind of closure, right? And if I take the closure procedure, then it's maybe a priori not clear. I could take a reduced structure or some kind of scheme theoretic closure or something like this, which actually is the same in this case. But maybe I ask you to postpone your questions after I formulate what is going to be the last theorem, which should tell you that you have maybe some kind of good control of these spaces of Galois representations and of the sheaves that I've wrote down. All right. So here's a theorem about the geometry of all these spaces. So first of all, xt, xb, and xb bar naive are rigid analytic Artin stacks. Of dimension, the dimension of T, respectively, the dimension of B, well, because, and the last one certainly is also the dimension of B. But it might have some irreducible components that are not met by XB itself. Okay, so then the second thing, XB and XB bar naive is open. And it's, let's call it schemes where the closure is reduced and a rigid analytic Artin stack. Okay, and it's a scheme theoretic image xb bar is reduced and a rigid analytic stack. Maybe I should have written the other way around, is a rigid analytic stack and reduced. Moreover, xb bar is normal and a local complete intersection. Okay, so you know pretty well what the local geometry looks like. The third statement is that if you take the projection map xb bar pi down to x qp2 times t hat, then this map is proper. And I caution you that unlike in the classical case of Greenfield, this is not true if you take away the second factor. Okay, the caution. This is not true for xb bar into x qp2. Okay, which is something which is kind of well known to people working with p-adic automorphic forms, because the image actually should be, well, the stacky version of the infinite fern of Gouvier-Maser. Okay, so it's kind of related to the fact that trainer representations or crystalline representations are dense in deformation spaces of Galois representations. Okay, so is it obvious that pi extends to x bar? Well, by definition, right? I mean, xb bar is contained in the naive compactification, and the naive compactification parameterizes d and the characters together with some condition. Okay, so by this map exists really by definition. So after 3, obviously there's 5. So 4. Let's try to analyze the boundary. The boundary of xb bar in xb bar is reduced and a Cartier divisor. Okay, so if I say it's reduced, then I should say it has a canonical structure. And the structure is the following. So this should be the kind of scheme theoretic support of the co-kernel of d1 into d, which kind of came up here. So I told you before that if the co-kernel, of the torsion part of the co-kernel. So if the co-kernel is flat over RA, then I would just be in XB, more or less by definition. So it's a scheme theoretic support of the torsion part of. Not so nicely put on the board right now, but kind of you should, like I hope I'm convincing you that saying something like this, which gives you a canonical structure as a closed substack. And this actually is reduced and a Cartier divisor. And I have some kind of Hodge-Tate decomposition. So I can take the universal, so let's say D over XB bar is the universal Fagara module. Okay, so then there is some, I can take the D-sen of D, which is just given by tensorizing over the rubber ring with CP. Okay, and then I should be able to decompose this. And what I'm doing here is I can take the alpha upper star of the line bundle corresponding to 1, 0, twisted by PP of well D1 And sorry. So it should have two parts, right? It should have a part which looks like CP twisted by D1, and it should have a part which looks like CP twisted by D2. And you might hope that both are line bundles, and that's actually true. And the line bundles can be described explicitly. So you pull back the line bundle 1, 0 and twist it by the boundary divisor. And here you take the alpha upper star of the line bundle 0, 1 and twist it by the negative of this. Okay. And finally, I'm sorry, I'm already over time. I want to say that this X B bar, which has a proper map into this X2. This certainly has a closed image. So this is a scheme-theoretic image. Okay, and let's call this maybe P prime over here. And I want to say that P prime is some kind of partial resolution of singularities of this guy. So it's proper birational. Pi prime is proper birational. It has geometrically connected fibers. And you can calculate that the R pi lower star of the structure sheaf is a structure sheaf. And certain other nice things. So this kind of a explicit geometric situation, which looks a little bit like the resolution of singularities, where you have very good control and where you actually can, in some sense, compute the sheaves involved in the construction before. Well, and I guess I should stop here. Sorry for going over time.